Hello. In my last lecture, I discussed about properties of colloids, in which we talked about physical properties like visibility, heterogeneity, etc. And then we looked at mechanical property, discussed Brownian moment, then about the optical properties where we covered Tyndall effect, and finally we looked at the electrical properties where we looked at electrophoresis, electroosmosis and the like. In today's lecture, I will discuss about the stability of colloids. What do you mean by flocculation and precipitation? What is exactly the difference between the terms that we use generally, coagulation or flocculation? Hardy-Schulze rule, flocculation value, methods of coagulation, protective colloids, gold number, and then towards the end I will summarize what we discussed today. Let me start with stability of colloids. We have already talked about this. Lyophilic salts are stable. Lyophobic salts are less stable. The reason for stability of the colloids is because of the existence of charges on the colloidal particles, and because of this charge, the colloidal particles repel each other. If we remove these charges by some means like persistent dialysis, the charges are removed, and because of this the particles can come close together, may form larger aggregates. In other words, they can precipitate out. Therefore, small amount of charge is always necessary for the stability of colloids. When the charges are removed, as they come out as precipitates, we can call it coagulation. There are two other terms that we generally use. One is flocculation, another is precipitation. What do you mean by flocculation? So, when the charges are removed and when the aggregates form, if the forces holding the particles within the aggregate is not strong enough, it is possible to redisperse the solid that has separated out into the colloidal state, which means flocculation is a reversible process. But if the interaction between the particles within the aggregate, that means the precipitates that are formed, the process is appropriately called precipitation, which is irreversible. We cannot redisperse the solid that has come out as precipitates back to the colloidal state. Flocculation or precipitation can be brought about by the addition of electrolytes. Why? The added electrolytes tends to neutralize the charges that are present on the colloidal particles, leading to destabilization of the dispersion. Electrolytes differ markedly in their ability to coagulate a colloidal dispersion, which follows what is called Hardy-Schulze rule. Some general observations have been made during the experiments with the electrolytes and their action on the colloidal dispersions. The coagulation capacity of an electrolyte depends upon the valency of the ion responsible for causing coagulation. And the second observation is that the ion responsible for causing this coagulation is the one which carries charge opposite to that of the charge present on the colloidal particles. Based on a detailed examination of the coagulation behavior of various electrolytes towards a particular sol, Hardy and Schulze suggested a general rule known as Hardy-Schulze rule. It is given in various statements. The first, coagulation is brought about by ions having opposite charge, which means negative ions cause coagulation of positively charged sols and positive ions cause coagulation of negatively charged sols. We can look at the examples. Ferric hydroxide sol is positively charged and hence can be coagulated easily by negative ions such as chloride, nitrate, sulfate, phosphate, etc. Similarly, arsenious sulfide sol, which is a negatively charged sol, can be coagulated by positive ions such as sodium, magnesium, barium, aluminum, etc. The efficacy of an ion to cause coagulation depends on its valency. We can see that efficacy of trivalent aluminum is much greater than that of magnesium ions, which are divalent, and that of sodium, which is monovalent. Efficacy of ferricyanide ion having valency of 4 minus is much higher than that of phosphate ion, which is trivalent, which is higher than that of sulfate ion, which is divalent, and in turn it is higher than that of chloride ion, which is univalent. Quantitatively, the efficacy varies directly as the square of the valency of the ion. Thus, magnesium ion is 4 times more effective than sodium, which is univalent. Similarly, aluminum ion, which is trivalent, is 9 times more effective than sodium ion in getting the flocculation done. The coagulating power of an electrolyte is usually expressed in terms of its flocculation value. We can define flocculation value as the minimum concentration in millimoles per liter of an electrolyte required to cause the coagulation of a sol. The flocculation values in millimoles per liter for the coagulation of negatively charged arsenious sulfide sol and positively charged ferric hydroxide sol are given in the table here. You can clearly see the names of the electrolytes: sodium chloride, potassium chloride, HCl, etc. The flocculating ion for arsenious sulfide sol, which is negatively charged, are positive ions: sodium, potassium, hydrogen, magnesium, barium, zinc, aluminum. And you can read the flocculation values which are given here. For the univalent ions which are given here, it is around 50, 52, 50, 30, 64. You can note the exception somewhere here where it is hydrogen ion. Then magnesium ion, which is much less, 0.72, 0.69, 0.68, and aluminum ion, it is 0.093. Similarly, if you look at the flocculation values for ferric hydroxide sol, where the flocculating ions are anions, bromide, chloride, nitrate, bromate, which are univalent, having values 138, 132, 132, very close to each other, with the exception of bromate ion, which is 31. And then we have divalent ions where it comes down to 0.315, 0.210, 0.238, and then finally for the ferricyanide ion here it is 0.096. It is seen that there are 2 exceptions: flocculation value of HCl for arsenious sulfide sol and that of potassium bromate for ferric hydroxide sol are relatively low. Why? Probably this is due to the strong adsorption of hydrogen ions in the first case and that of bromate ion in the second case. A smaller flocculation value indicates the greater coagulating power of the given electrolyte. That means the coagulating power of the electrolyte is inversely proportional to flocculation value. How to bring about coagulation? One method we have already talked about and mentioned also, persistent dialysis, but most commonly used method for causing coagulation of a colloidal solution is the addition of an electrolyte. However, the coagulation of a colloidal dispersion can also be achieved by any of the following methods that we can look at. One is by electrophoresis. Electrophoresis is the phenomenon which we have discussed earlier, where the colloidal particles migrate under the influence of an electric field to the electrode of opposite charge. When they reach the electrode, they get discharged, resulting in the coagulation of the sol. We can also bring about coagulation by mixing two oppositely charged sols. When we mix oppositely charged sols, the charge of one sol neutralizes the charge present on the other sol, thereby bringing about neutralization and leading to coagulation of both. As I mentioned, persistent dialysis. You can continuously dialyze the given sol in order to purify it. That means you want to remove the impurities that are present in the sol, and when you do so, if you do it excessively, all the ions that are necessary for the stability of the sol are removed, thereby bringing about coagulation. In other words, you should be very careful in purifying the sol. You should not go for persistent dialysis leading to coagulation. We have seen that lyophobic sols, such as those of metals, are very unstable. They get easily coagulated in the presence of small amount of electrolytes. This reduces their shelf life as well as restricts their usage. Contrary to this, lyophilic sols are much more stable and do not get coagulated easily under similar conditions. Even when small electrolytes are added, they may still remain stable. The reason for this is that there is very strong interaction between the particles and the dispersion medium. Probably a thin envelope of the dispersion medium protects the particle, thereby preventing it from getting coagulated. It is found that if we add a small amount of lyophilic colloids such as gum arabic, gelatin, starch, etc., they impart stability to the hydrophobic sols towards the coagulation when electrolytes are added to them. They get protected by the lyophilic colloid. That means they shield the particles of lyophobic sols from the attack by the electrolytes and thereby prevent the coagulation. The lyophilic colloid, which is added to a lyophobic colloid in order to prevent the coagulation, is therefore called protective colloid. The exact mechanism of protection is not very clearly understood, but it is believed that the lyophilic colloid particles get adsorbed on the surface of the particles of the lyophobic sol, forming an envelope around it and thus protect them from the action of the electrolyte, as can be seen in this figure. You have a large particle of lyophilic sol. The lyophilic sol that is added to the system gets adsorbed onto the surface, thereby preventing the attack by the electrolytes, which prevents the lyophobic colloidal particles from coming into contact with each other, thereby preventing the particle growth and hence preventing coagulation. Gold number. The protective power of a lyophilic colloid is usually expressed in terms of a number called gold number. This was introduced by Zsigmondy, who has worked extensively in colloidal state. Now, why gold sol is chosen? Because it is a lyophobic colloid and we can actually study how it gets coagulated in presence of different electrolytes. So, lot of experiments were carried out by Zsigmondy and he studied the amount of electrolytes required to bring about coagulation of the gold sol, and he came out with what is called gold number. The gold number can be defined as the minimum amount in milligrams of the dry material from which the lyophilic sol is prepared, which is just sufficient to prevent the coagulation of 10 ml of a standard gold sol on the addition of 1 ml of 10% sodium chloride solution. The standard gold sol is used, whose concentration is between 0.0053 to 0.0058%. How do you recognize the change that is taking place? It is the color of the gold sol changes from red to blue. That means it is getting coagulated, the particle size increases, and therefore color changes from red to blue. And we know that the colloidal particle size decides the interaction of these particles with the electromagnetic radiation in the visible range. The size and color are related, and therefore it was easy to study the effect of electrolytes and the protective action of the lyophilic colloids. And by extensive experiments, he found out the gold number values of various lyophilic colloids. The values of the gold number here, and we can say that smaller the value of the gold number, greater is the protective power of the protective colloid. Some of the lyophilic colloids that are used extensively, you can see here gelatin, for which the gold number is very low, 0.005 to 0.01, casein 0.01 to 0.02, hemoglobin 0.03 to 0.07, egg albumin 0.08 to 0.10. This tells us that the gold number is very low, therefore these are very efficient in protective ability when they are added to lyophobic sols. When compared to that, starch has a gold number value of 20.25, orders of magnitude higher. Therefore, ability of starch as a protective colloid is very poor, and hence these are the ones which are extensively used in the protective action. Now let me recapitulate what we studied today. Stability of colloids, why lyophilic sols are stable and why lyophobic sols are unstable. Flocculation and precipitation, what do you mean by flocculation? Similarly, based on that study, the rule that is framed, Schulze-Hardy rule, or sometimes called Hardy-Schulze rule, and based on that we get the flocculation values, which are quantitative measurements to compare the abilities of electrolytes in bringing about coagulation, and then methods for bringing about coagulation of the sols. What do we mean by protective colloids? That means how to impart stability to the lyophobic sols which are inherently unstable, and then gold number, which is a quantitative measurement of the protective action of the lyophilic sols. In my next lecture, I will discuss in detail two important colloidal systems, that is emulsions and gels.